Welcome back. So today we are discussing the module number 4, direct stiffness method. This is the continuation of the third module, stiffness method. So in stiffness method, we learn to solve the problems of a structure by writing the individual elements and then assembling it to a big structure. So in the direct stiffness method, we are formulating one correlation between the element as well as the global coordinate or as a structure, and that will be used for writing the direct stiffness for solving the problems. So the introduction to direct stiffness method, we have two coordinates. First is a global coordinate and a local coordinate. We will be learning the same in the coming slides. Then the rotation of the axis in two dimensions. So we just briefly explain. There is so pointer and I have a frame with fixed ends, and so I have an individual beam columns as well as a beams, and each individual beam or column will have its own axis, its own local coordinate, and there will be a global coordinate xy for the total structure. So if we're considering this right column alone, this column will have some x coordinate and it will have some y coordinate. So basically we are relating the element coordinate with the global coordinate, and hence the rotation of axis will come into play in this one due to these translations. And the stiffness matrix of elements in global coordinate from the element coordinates has to be formulated first, and then assembly of the load vector and the stiffness matrix. The solution of the two numerical problems of two span continuous beam, single bay, single story portal frames, etc. we will be learning in this module. The formalized stiffness method involves evaluating the displacement transformation matrix CMS correctly. So our aim is to find the CMS, and generation of the matrix CMS is not suitable for programming. Hence we have evolved in a direct stiffness method which has got the correlation between the local coordinate and the global coordinate. Also in the direct stiffness method, we need to simplifying the assembling process of stiffness of the structure SS, the assembled stiffness structure stiffness matrix. The key is to this is to use the member stiffness matrix for all actions and displacement at both ends of the member. If the member displacements are expressed with reference to the global coordinate, the process of assembling the SS can be made simple. So what I'm telling is that if you have a beam or a frame with two columns and a beam, each individual columns as well as a beam will have its own displacement in its own local coordinate. So if you are writing the displacements as well as the actions with respect to the global coordinate, even for a single structure, that thing can be added to get the behavior of the total structure. Okay, so this will make you clear. So we have the member oriented axis, which is called as a local coordinate. Suppose you have a bar like this, the local coordinate will be the x along the length of the bar and y will be vertical, and for a delta L will be the axis deformation of the bar. But in reality, or in different structures, this can be an inclined one. The bar can be placed in an inclinedly in the space, so that the bar will have its own local coordinate, and there will be a global coordinate which is known as capital XY, which has to be taken as the global one, and we need to find all the equations of the individual elements with respect to the global coordinate, so that we can add it to find the total response of the structure. That means the small xy will be the element coordinate and capital XY will be the global coordinate. So for a delta L movement, the corresponding movement in the horizontal direction, that is actually in the x, will be delta L cos theta, and corresponding movement in the global coordinate y will be the delta L sin theta. So this delta L is in the local coordinate, and this delta L sin theta and delta L cos theta will be in the global coordinate. So we have written the displacements of this element with respect to the global coordinate. Suppose if we have say some 2 or 3 bar, all the individual bar will have its own element coordinate. You should write the element coordinate, or should convert the coordinates values of individual element coordinate to the global coordinate, so that you can just add for the element 1 plus 2 plus 3 to get the global coordinate values. Hope it's clear for you. And the structure oriented axes are called as the global coordinate. Now we are moving to some formulations. As the first one, plane truss member. So for the truss member, always note that there is no rotation. There will be the displacement along the axis, as well as vertical displacement for the both ends of the truss member, and the stiffness coefficients in the local coordinate are given as 1, 2, 3 and 4, which are the degrees of freedom for the joints. And to find the stiffness, we know that we are providing a unit displacement and we are measuring the forces at various coordinates, right? So same thing is done here. We are applying a unit displacement in the first direction, and we are measuring the various forces at 1, 2, 3 and 4 for the first case. And for second case, I should apply for the 2 a displacement, and the corresponding forces at the different coordinates has to be measured. For the unit displacement corresponding to degree of freedom 1, it is this case, when it is actually axially moved, the stiffness will be EA by L, which is a non-valid rule. Okay, and you also know that when this is actually in movement, all the other displacement should be restrained. So this will be restrained so that an equal and opposite force of EA by L will be created at the right side. There is no vertical movement here, there is no stiffness coefficient for the 2 and 4. So those things are written for the first line. So this will be 1, 1, 1, 2, 1, 3, 1, 4. Right. And if you again apply the displacement for the coordinate 3, that is actually applying from right to left, that is applying in this direction. We have corresponding minus EA by L 0, EA by L 0 as the stiffness coefficient. So this will be the member stiffness matrix in the its own coordinate called as a local coordinate SM. Now as we have discussed, we have to convert the local coordinate values to the corresponding global coordinate values. Okay. So for that, you should note that the displacement in the global coordinate are given as U1 and U2, and displacement in the local coordinate are D1 and D2. So from this figure, it's clear that the global axes are denoted here as the capital XY, and the local axes are, one is along the member small x and y is vertical. So when this member is actually getting stretched, right? There are four displacements possible: d1 linear movement, d2 vertical movement, d3 linear movement at the right point, and d4 is the corresponding not the other vertical movement. So these are the possible movements for the plane truss member. We know xy local axis and capital XY are the global axis. So what we are going to do that is that we are going to find a relation between the d1, which is displacements general d, which are the displacement in the local coordinate, with the u, which are the displacement in the global coordinate. So here we have to find the u1, u2, u3 and u4. For that one, let's first focus on the u1. So for that, u1 is equal to u11 plus u at 1 due to the application of 2. Alright, and u2 is equal to the displacement at the second point due to the application of u21 will be the corresponding displacement in the second point due to the change in the first point, plus u22. So we have to find the individually u12, u11, u22 and u21. So to solve for that, you should first clearly understand this picture. That is, a theta is given to you, which is the angle made by the plane truss with the global axis, which will be the theta value. So provided this is theta, let's consider this triangle. If we consider this triangle for a d1, that is an linear movement in along the small x local coordinate. For this one, the corresponding horizontal displacement will be the cos theta, will be the d1 cos theta, and the corresponding movement in the vertical, which is given as this, will be minus d2, sorry, it will be d1 sin theta. Okay, so it will be the displacement at the second coordinate, y coordinate, with the application of displacement in the first coordinate. So the u11 and u21 is found from this triangle. Similarly, you want to find for the u22 as well as u at 1 due to 2. So it will be u12 also. So to find that one, you should solve for this triangle also to get the values as d2 cos theta and minus d2 sin theta. Okay, so when you solve this triangle, you will get this angle also theta. So you can measure the various coordinate value, that is upon a movement of d2, the corresponding horizontal displacement and the vertical displacement can be found. And hence u1 is equal to u11 plus u12, displacement at the first point, So to the moments in one as well as the second point, and u2 is equal to u21 plus u22. So we are writing all the values, substituting to get the corresponding values, and we are making it into a matrix format. And then d1 d2 will be the just inverse of this one. It will be cos theta sin theta minus sin theta into u1 u2. So we have d is equal to ru, where r connect the global coordinate with the local coordinate displacements. So considering the both ends, so we have discussed only for the left end. Same replica will be happening for the right end also. Clubbing all those things will give you cos theta sin theta, cos theta sin theta minus sin theta cos theta. It will be replica. So d is equal to the matrix into u matrix. So d local is equal to rt into d global. So we are writing the rt is equal to, we are making this one as a single matrix is called as the r. Okay, r is here, and zero matrix, null matrix, zero matrix, and the r matrix will be the rotation matrix, which will connect the local displacement with the global displacement. Now we are into the transformation of the load vector. So in the previous slide we have learned how to transform from the global coordinate with the element coordinate. For the transformation of the load vector, instead of d and u, we have actions in local coordinate given by a1 and a2, and actions in the global coordinate given by the f1 and f2 in place of u in the displacement case. Okay, so we know f1 is equal to f11 plus f122, f2 is equal to f21 plus f22. So here also we are doing only for one side, and then we will club it later. So for an unit movement along the line, the corresponding f1 will be a1 cos theta, which will be similar to the d1 cos theta. Also f21 is equal to a1 sin theta. And also f22 is equal to a2 cos theta, and f12 is equal to minus a2 sin theta. So these sign changes will happen due to the tension and compression. Once you have plotted that one, you will be finding how the whether the element is actually shrinking or it is actually expanding, which will give you the signs. Okay, so f1 is equal to cos theta minus sin theta cos theta in the a1. Then relating a and f. So previously we had d is equal to r into u. Here we have a is equal to r into f. As previous, we are writing for the entire member. So a is equal to matrix r into a global, or result f. So we have obtained transformation for the stiffness matrix A local is equal to Sm into D local. So this was the individual element stiffness matrix which we have discussed. Yeah, here. Yes, sir. Sorry, here. And then again expanding, a local is equal to RT into a global, which we have just seen. is equal to Sm into D local is equal to RT into D global. This is actually the expression. Then again A global is equal to RT to the right side, RT inverse into Sm into RT into D global. So A global is equal to, this is actually SMS into D global, where SMS is equal to RT transpose, which will be equal to the inverse into Sm into RT. So this is actually both the same. And the which will be the member stiffness matrix in the global coordinate. So we have SMS, which is the member stiffness matrix in the global coordinate. Sm will be the member stiffness matrix in the local coordinate. Okay. You can also remember as like Sm will be the local one, Sm S will be for the structure. It's actually global coordinate. So we have SMS is equal to RT into transpose into Sm into RT. Writing all those, we will just represent the C cos theta, S is sin theta. So all those things are simply written, and all the values substituted. To find EA by L into C square CS minus C square C minus EA. So this equation has to be, or this matrix has to be remembered, which will be the element stiffness matrix in the global coordinate. So suppose you have three truss member. So for the member 1 you have this matrix. If you substitute the values, you will get the global coordinate values of the member 1 plus global coordinate values of member 2 plus 3 will give you the total structure member stiffness. Okay, so these are the member stiffness matrix in the global coordinate for a plain truss member. So this was a derivation, which is an important one, and you are supposed to remember this one, these values. Go to this one. So you can see some similarities that always these values are same. This matrix and this matrix is same, and also this one is also same. So the suppose 1, 2, 3, 4. 1 and 4 is same, and 2 and 3 is same. So you should remember only 1 and 2 so that you can make the entire matrix. The next one is the plane frame member, and writing the stiffness coefficient in the local coordinate will be a big matrix, because degree of freedom for 1 and will be 3, then writing also 6. So 6 by 6 matrix will be the individual element stiffness matrix. Okay, so the problem is getting more difficult or more complex. It's a member stiffness matrix in the local coordinate. And the corresponding transformation of the displacement vector will give you D is equal to R into T into D global. So you should note one term is coming here, one term is coming here on comparison with the previous matrix. So those value, or the one is with respect to the moment, is 3 and 6 here, correspondingly the 1 came in the matrix. So again writing is as R. So now the R matrix will be a big matrix of 3 by 3, and there will be null matrix, this one, and 0 matrix and R matrix. So this will be the R rotation matrix, which relates the local displacement to the global displacement. Similarly, the transformation of load vector A local is equal to RT into A global. Here also the majority the value is the same, and additionally the 1 will come. the transformation of the stiffness matrix A global is equal to SMS into D global. So this is actually the same equation which we derived for the plane truss member case. SMS is equal to RT transpose into SM into RT, which is the member stiffness matrix in the global coordinate. Called SM will be the local coordinate, SMS will be the structure coordinate, it's the global coordinate. Okay, so this was the SM value, and this was the RT value with additional unit values. And it will be a big matrix to solve and get the SMS. Okay. Stop for today.